All right, so now that we've talked about some polynomial vocabulary, let's sort of talk about what their graphs will look like. So we'll make some connections from equations to graphs. We'll use the word degree often. We'll use the word leading coefficient. And so we'll start by making some connections between the degree of the polynomial and what that tells us. So the degree tells us that the maximum number of times that the graph could cross the x-axis. So an example of that could be if I have something that has a degree of 2 and x squared, I could have x squared plus 4x plus 5, which may look something like this, and it's actually not going to cross the x-axis at all. I could have a parabola that crosses the x-axis 2 times, or I could have a parabola that has its vertex on the x-axis and looks like it only touches the x-axis once. So the degree tells us the maximum number of times the graph could cross the x-axis. So something that has a degree of 3 could potentially cross the x-axis 3 times, and that could look something like this, right? So here's 1, 2, and 3. It could also look something like this and only cross the x-axis once. So our degree also tells us something about the end behavior of the polynomial. And so we talked about end behavior in the beginning of this year when we talked about functions. So even degree polynomial, so talking about something that's like x cubed, x to the 4th, any time where my degree here is going to be an even number, they have, in sort of non-technical math terms, they have matching arrows in the end. So looking at my parabola, both of these arrows here are going up. So for even degree, the lead coefficient sign determines if the arrows are going up or if they're going down. So if my lead coefficient is positive and I have an even degreed polynomial, then my arrows are going up. If it's negative, then my arrows are going down. So sort of similar for odd degreed polynomials, mean the two end arrows don't agree in directions. So something like, let's go back here to my pen. So something like x cubed, we said could look something sort of along these lines here. So they don't agree in the direction. So one of these is going up, one of these is going down, and my lead coefficient will determine whether or not it's going up here and down here, or if it's going up in this quadrant and sort of down in this quadrant here. So let's go through and do a few examples. So here I would say this is a polynomial that has an odd powered degree. So this could be something like x cubed. And because I'm positive, positive, and negative, negative, I know that this is a positive lead coefficient. So here, the degree of this polynomial is 4, and I have a positive 1 as my lead coefficient. And I know that this could potentially cross the x-axis 4 times, so a really rough sketch of this parabola would look something like this. Since we're just asking for the end behavior, we're just going to say that as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y also approaches infinity. So there's the end behavior just by looking at that equation, or at that function. Moving forward, we can give another rough sketch. The degree of this polynomial is 2 because the largest exponent is 2. And I can see here that I have a negative lead coefficient. So I know that my end behavior will end up looking something like this. We don't know if this crosses the x-axis twice or 1 time or no times, but we're just looking for the end behavior here. So as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y also approaches negative infinity. So again, I have an even degreed polynomial, so both my end behaviors are matching, and my lead coefficient told me that they were both going down. So here, I have 4 as the degree of the polynomial, and I have a positive lead coefficient, positive 1 here. So I know that my end behavior will both be going up. So as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y also approaches infinity. So here, my end behavior, I would say that this end behavior belongs to a cubic function. It could potentially belong to a cubic function because I'm crossing the x-axis 3 times here. And that my lead coefficient is negative because over here I'm going down. So as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches infinity. So here, I would say that this potentially belongs to a x to the 4th power. So it's even, they're both going up. And I also know that my lead coefficient is positive. So as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches infinity. So there are a few more examples here. I know that this one is odd and positive lead coefficient, so I'll be going up and down like this. Here, this could potentially belong to something that's cubic, that has a negative lead coefficient, so negative x cubed. And again, when I say this belongs to something like this, there are lots of other terms that are within this polynomial, but this piece really gives us some insight as to what the end behavior will look like. So let's just go through and consider the following polynomial. So we'll go through some of those vocabulary words that we talked about in the last lesson. How many terms does this polynomial have? 1, 2, 3, 4. This has 4 terms. What's the degree of the polynomial? So this polynomial, and I know this question is coming up soon within these slides, it's not written in standard form. So just because this is the term that comes first doesn't necessarily mean that that's the degree of this polynomial. So again, the degree is the largest exponent, which is 3. Consider the following polynomial. What's the maximum number of possible roots this could have? The degree of the polynomial is 3, so that's the maximum number of times that this could potentially cross the x-axis. Is it written in standard form? It is not. If I were to put this in standard form, we would start with the largest exponent, so 2x cubed, and we would just work our way down. Minus 5x squared plus 2x plus 20. So now this is written in standard form. I have my lead coefficient, the degree of the polynomial is first, and my constant will always come last. What's the end behavior? So here I have a positive lead coefficient and I have an odd degree. So I know that this will be a function that in the very end will probably look something like this. So as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches negative infinity. What is the coefficient of its linear term? I would say this is my linear term, and the coefficient there is 2. What is the constant term? I would say this is my constant term. It's the term in the polynomial that isn't paired with any other variable. So my constant term is positive 20. Whoop. What is the lead coefficient? So my lead coefficient is not this number right here. It's the number that's paired with the largest degree. So the lead coefficient is 2. And it's not talking about this 2 right here, which could be a little bit misleading. It's talking about this value 2. How many possible roots does this have? So here's an example of a polynomial that's written in factored form, and I know that this could potentially have 2 roots, and it does have 2 roots, and we can actually solve for them. But here I have these 2 sort of chunks or factors of my polynomial. I could say that x minus 4 is equal to 0, or 2x plus 3 is equal to 0. So x is equal to 4, that's one of my roots, and x is equal to negative 3/2. That's my other root. So this is a quadratic. My lead coefficient here is positive. So I know that my end behavior would be as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches infinity. So here I was multiplying these two factors, each had an x in them, so I knew this would look like something x squared if I were to expand this polynomial. So let's go back and look at this. Consider the following polynomial. So when we're talking about graphs of these polynomials, my degree is how many times am I multiplying x together here? I'm multiplying x together twice. So my degree is 2. And we just talked about the end behavior. I have a positive lead coefficient. So as, not x, that's funny. As x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches infinity. We just solved this for my roots here. So we said x is equal to 4 and negative 3/2. And my y-intercept, I can always figure out the y-intercept of any polynomial by plugging in 0 for x. So g of 0 is 0 minus 4 times 2 times 0 plus, let's make that a plus, plus 3. So this will be negative 4 times positive 3, which will give me negative 12. So if I really wanted to, and is it going, no, it's not going to have me do this. If I really wanted to, I could come down here to negative 12. That's my y-intercept. Over here at 4, here is one of my x-intercepts. And at negative 1.5, here's my other x-intercept. So this is certainly not drawn to scale because it does not look like my x-axis, or sorry, the vertex. This is not the vertex. So the vertex will be somewhere sort of exactly halfway between these two roots. And I can go ahead and sketch in sort of a really, really rough sketch of what this polynomial would look like. So I can see the degree is 2, and it in fact does touch the x-axis twice. So I just want to talk quickly about giving a rough sketch of a polynomial versus drawing a graph of a polynomial. So a rough sketch, we need some roots, some end behavior, the general shape, and the y-intercept. So I would say this is a very rough sketch. Drawing graphs, it looks like it's very formal graph, so there's lots of exact points where we're connecting the lines there. So if I were to draw this graph up here, I would want a lot more values. I would certainly find the vertex and the axis of symmetry. I would find a lot more values to go ahead and plug into this function in order to get a more exact graph. So here I have a polynomial, so the directions are to graph it up here. So the degree, how many x's am I multiplying together? The degree of this is 3, and my lead coefficient is a positive 1. So I know my end behavior will be as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. So I know, just sort of rough sketch here, my end behavior will end up looking something like this. My roots, if I set each of these pieces equal to 0, I can solve for my roots. So my roots are at negative 3, positive 4, and positive 9. So negative 3, so I know I have a root here. Positive 4, 1, 2, 3, 4, I know I have a root here. 5, 6, 7, 8, and 9. So those are my 3 roots. And my y-intercept, if I were to go ahead and plug in 0 for x here, I would have a 0, a 0, and a 0. And so what I can go ahead and do is I can say, what is 3 times negative 4 times negative 9, and that's going to give me positive 108. Because here I have 3, 0 minus 4 gives me negative 4, 0 minus 9 gives me negative 9. So negative 4 times negative 9 will give me a positive number, and that times 3 will give me 108. So I know that my y-intercept will be way, way, way up here somewhere. But for now, I can just go ahead and sketch in what this graph could potentially look like. So it looks like I know I'll be starting down here. My y-intercept will be way up there somewhere. I can come down, and then I know I'm swooping back up. So a few things that I don't know. I don't know sort of, is this tight down here? Is this really swoopy down here, right? So that's another reason why this is just a rough sketch. I also don't necessarily know the steepness of these lines or where this sort of falls. So again, as we're rough sketching these, we're really focusing on the end behavior, the roots, and the y-intercept. So those are the pieces that we're really focusing on. So my degree here, so let's take a look at this one and we're graphing again. My degree, I'm asking myself, how many times am I multiplying x together? Here I have x minus 5 times x minus 2 times x plus 6 squared, which is really x plus 6 times x plus 6. So really I'm multiplying x 1, 2, 3. This has a degree of 4. So I know that my end behavior will be matching. I don't have a negative value out front here. So as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches infinity. My roots will be at 5, positive 2, and I'll have what we can call a double root at negative 6. So here, because I have a double root here, because this is squared, this really means that I have a root of x minus 6 twice. So as I'm sketching this in, and we'll go to my y-intercept here. So that'll be the last piece. So I have 0 minus 5, 0 minus 2 times 0 plus 6 squared. So this will give me negative 5 times negative 2 times 6 squared. So this is going to be 36 times negative 2 times negative 5, which will give me 360. So again, another very large y-intercept here. So I know that my end behavior will each sort of end up going up like this. My roots are at 2, 3, 4, 5. And then I have a double root at negative 6. So 1, 2, 3, 4, 5. A double root at negative 6. And my y-intercept is going to be way up here at 360. So sketching this in, I know my end behavior starts here. A double root means that it will bounce at that root there. And let's actually go ahead and make this look a little curvier like it should be. So it will come down, it will bounce at that root and come back up. Go through my y-intercept of 360, and then the other roots it will pass through like it has before. So here, come back up, and again, we don't know sort of how low this goes, if it comes way down and goes back up. There's a lot that we don't know, but we do know that this is sort of a general sketch of what my graph will look like. So that is some practice with graphing polynomials that are in factored form. You'll notice that I uploaded a practice sheet for you, and I also uploaded the answer key, so you can go ahead and practice doing some of these problems on your own.